The edge of the observable universe is 46 billion light-years away in every direction. Every direction. That is not a poetic description of how vast space is. That is a precise mathematical statement about the structure of the cosmos. The universe, according to every model built by every cosmologist working over the past 70 years, should look identical no matter which direction you point your telescope. Same density of galaxies, same temperature of background radiation, same distribution of matter across the sky in every direction simultaneously. Perfect symmetry, perfect uniformity. A cosmos with no preferred direction, no special axis, no up or down or left or right. That is what the models predict. That is what the physics demands. And that is exactly what astronomers expected to confirm when they mapped the oldest light in existence. Instead, they found something that should not be there. Something that has no explanation inside the current framework of cosmology. Something that suggests the universe we can see may be only a small part of something far larger, far stranger, and pulling on everything inside it from beyond the edge of what we can ever observe. To understand why what they found is so disturbing, you need to understand what the cosmic microwave background actually is. 13.8 billion years ago, the universe began in a state of unimaginable heat and density. In the first moments after the Big Bang, space was so hot that light could not travel freely. Photons were constantly colliding with charged particles, scattering in every direction, unable to move more than a tiny distance before being absorbed and re-emitted. The universe was opaque. Then, approximately 380,000 years after the Big Bang, something changed. The universe had expanded and cooled enough that electrons and protons could combine into neutral hydrogen atoms for the first time. The moment that happened, the universe became transparent. Light that had been trapped suddenly had a clear path to travel. It streamed outward in every direction simultaneously and has been traveling through the expanding universe ever since. That light is the cosmic microwave background. It is the oldest light in existence, a snapshot of the universe at 380,000 years old, stretched by 13.8 billion years of cosmic expansion into the microwave frequency range, now surrounding us in every direction like the faint afterglow of the fire that started everything. When astronomers map it, they are looking at the universe in its infancy, and what they see in that map is the problem. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, known as WMAP, into space, specifically to map the cosmic microwave background with greater precision than had ever been achieved before. The satellite settled into a stable orbit and began scanning the entire sky, measuring the temperature of the background radiation in every direction with extraordinary sensitivity. The expectation was confirmation. The models predicted that the CMB would show tiny random temperature fluctuations spread uniformly across the sky, the microscopic seeds of the large-scale structure of the universe, distributed with no particular pattern and no preferred orientation. What WMAP found was almost that. Almost, but not quite. The temperature fluctuations were not perfectly random. When astronomers analyzed the largest scale patterns in the CMB map, the structures that stretched across significant fractions of the entire observable sky, they found something deeply unsettling. The patterns were not symmetrical. One side of the sky was measurably different from the other, not in a small, marginal, possibly just measurement error kind of way, in a statistically significant, reproducible, confirmed by multiple independent instruments kind of way. The universe, at its largest observable scales, had a direction, and in 2005, the cosmologists studying this anomaly gave that direction a name that reflected exactly how seriously they were taking it. They called it the axis of evil. The name was not chosen carelessly. It was chosen because the existence of a preferred axis in the cosmic microwave background is not just an interesting curiosity. It is a direct challenge to the cosmological principle, the foundational assumption on which the entire framework of modern cosmology is built. The cosmological principle states that the universe is isotropic, meaning it looks the same in all directions, and homogeneous, meaning it has the same properties at every location. These are not minor technical assumptions buried in the fine print of cosmological models. They are the bedrock on which everything else is constructed. The equations that describe the expansion of the universe, the models that predict the distribution of galaxies, the calculations that tell us the universe is 13.8 billion years old and composed of roughly 5% normal matter, 27% dark matter, and 68% dark energy. All of it rests on the assumption that there is no special direction in the universe, no axis, no preferred orientation. The axis of evil, if it is real and not a measurement artifact, does not just add a footnote to cosmology, it pulls the foundation out from under it. What made the finding impossible to dismiss was that it didn't come from a single instrument or a single team of researchers. 3 separate space telescopes independently confirmed the large-scale alignment in the CMB, and the alignment itself was stranger than simply one side being slightly warmer or cooler than the other. The large-scale structures in the cosmic microwave background appeared to be aligned with the plane of our own solar system, the ecliptic plane, the flat disk in which Earth orbits the Sun and in which all the planets of our solar system move. The probability of this alignment occurring by random chance was calculated to be extraordinarily small, and it made no physical sense whatsoever. There is no known mechanism by which the local geometry of our own solar system, a tiny structure measuring a few light hours across, could have any relationship to patterns imprinted on the cosmic microwave background 13.8 billion years ago, across scales of billions of light years. The two things should have absolutely nothing to do with each other. The fact that they appear connected is either the most extraordinary coincidence in the history of scientific measurement, or evidence that something fundamental is missing from our understanding of the universe. And the CMB alignment wasn't even the only anomaly the surveys were finding. In 2004, astronomers studying the cosmic microwave background map in detail identified a region of the sky that was significantly colder than everything surrounding it. Not a small local variation, but a massive cold region stretching across almost 2 billion light-years of the observable sky, a feature so large and so anomalously cold that it immediately attracted attention from researchers trying to understand what could possibly have caused it. The leading candidate explanation was a supervoid, an enormous region of space almost entirely empty of galaxies, where the relative absence of matter would cause photons passing through it to lose energy and appear cooler by the time they reached our instruments. Astronomers searched for the supervoid and eventually found evidence of an unusually empty region in the same area of sky. But here's where the story refuses to resolve neatly. The cold spot they found was not large enough or empty enough to fully explain the temperature anomaly in the CMB. The cold spot was colder than the void alone could account for. Something else was contributing to it, something that has never been satisfactorily identified. And the cold spot sits in approximately the same broad region of sky as the axis of evil alignment, which raised an obvious and deeply uncomfortable question. Were these anomalies connected? And if so, what single cause could produce all of them simultaneously? The answer that some researchers began seriously considering was the one that the standard model of cosmology had no framework to accommodate: something outside the observable universe. The observable universe is a sphere 93 billion light-years across, centered on Earth, defined not by the physical edge of all existence, but by the distance light has had time to travel since the Big Bang. Beyond that boundary, there is almost certainly more universe, possibly vastly more, possibly infinite more. We can't see it because the light from those regions has not had enough time to reach us yet. But just because we can't see something doesn't mean it can't affect us. Gravity has no speed limit imposed by the cosmic horizon. If structures of sufficient mass existed beyond the observable boundary in a particular direction, their gravitational influence in principle could reach across the horizon and pull on the matter inside our observable universe. And in 2008, a team of researchers led by Alexander Kashlinsky at NASA published a paper claiming to have found direct evidence that this was happening. They called it dark flow. By studying the motion of galaxy clusters across a large region of the sky and carefully subtracting all known sources of motion, they found a residual coherent drift. Hundreds of galaxy clusters spread across
Something is moving through our solar system right now, and it is not behaving the way anything natural should. It has been tracked, photographed, and analyzed by some of the most sophisticated instruments humanity has ever built. And the more data that comes in, the harder it becomes to explain using the rules we thought governed everything out here. Its name is 3I/ATLS, and what the JUICE spacecraft just confirmed about it has quietly divided the astronomical community in a way that almost nothing in recent memory has managed to do. Let's start with the thing that nobody has a clean answer for. Deep in the outer solar system, nearly 420 million kilometers from the sun, where temperatures drop to around -150 degrees Celsius, and where the solar energy reaching any object is so weak it can barely power a small light bulb. 3I/ATLS is firing jets, not one jet, 3 jets, spaced exactly 120 degrees apart from each other, with a geometric precision that made the researchers who first measured them go back and check their instruments before they published anything. The jets are still active, still symmetrical, still burning with a consistency that has not changed since the object was first detected. And according to everything we know about how comets work, that should be physically impossible. To understand why that matters, you need to understand what a comet jet actually is and what it requires to exist. When a comet travels close to the sun, solar radiation heats its surface and causes frozen volatile materials, water ice, carbon dioxide, carbon monoxide, to rapidly convert from solid directly to gas in a process called sublimation. That expanding gas blasts outward from the surface, carrying dust and debris with it, creating the visible jets and the glowing coma that surrounds active comets. It is a heat-driven process. It requires energy input from the sun to function. Beyond approximately 2.5 astronomical units from the sun, roughly 2.5 times the distance between Earth and the sun, solar energy drops off so dramatically that this process should slow to almost nothing. Water ice becomes essentially inert at these temperatures. The gas pressure required to drive visible jets should simply not be able to build up. Most comets that travel this far from the sun become dark, frozen, inactive objects drifting silently through space. 3I/ATLS is 420 million kilometers from the sun. It is well beyond the point where its jets should have died. They have not died. They have not even weakened in any measurable way. They are still firing with the same intensity and the same perfect geometric spacing that was recorded when the object was first observed. No standard model of cometary physics explains this. On March 3rd, the JUICE spacecraft, the European Space Agency's Jupiter Icy Moons Explorer, currently in transit toward the Jovian system, captured new observational data on 3I/ATLS from a distance of approximately 400 million kilometers. The images confirmed what the ground-based observations had been showing. The jets were still active, still symmetrical, still perfectly spaced, but the JUICE data added something new to the picture that the ground-based telescopes had not been able to resolve clearly. The ionized glow surrounding the object, the coma of charged particles and gas that envelops it like an electric halo, had intensified since the previous observation window, not slightly, measurably, significantly enough that the JUICE science team flagged it immediately in their preliminary data report. An intensifying coma at this distance from the sun, in an object whose jets should already be dead, pointed toward an energy source that the sun was not providing. Something else was powering this object, and nobody had a consensus explanation for what that something else was. Then the instruments ran into something they were not designed to handle. When the JUICE spacecraft's ultraviolet spectrometer attempted to scan 3I/ATLS to analyze its chemical composition, a routine procedure that would normally produce a clean spectral fingerprint identifying the materials present in the object's coma, the scan failed, not because of a technical malfunction, not because of a software error. The telemetry data showed detector saturation. The instrument was overwhelmed by an incoming signal that was far stronger than any natural reflection or emission of an object of this type at this distance should have been capable of producing. When the engineering team analyzed the frequency at which the saturation was occurring, they found it centered near 1665 megahertz. That frequency is not arbitrary. It is not a random number buried in a technical report. 1665 megahertz is one of the characteristic emission frequencies of the hydroxyl radical, OH, a molecular fragment produced when water molecules are broken apart by ultraviolet radiation. Hydroxyl emissions at this frequency are well documented in the study of comets and interstellar chemistry, but the intensity of the signal that saturated JUICE's detector was orders of magnitude beyond what any known natural process occurring at this distance from the sun should have been capable of producing. While the instrument teams were working through the implications of the detector saturation, the orbital dynamics researchers were sitting with a number that had been bothering them since the object's trajectory was first precisely calculated. The orbit of 3I/ATLS is tilted 8.8 degrees from the ecliptic plane, the flat disk in which the planets of the solar system orbit the sun. An 8.8 degree inclination is not unusual for a comet in isolation. What made this particular number extraordinary was what it aligned with when the trajectory was projected tilted forward toward Jupiter. Jupiter's magnetic axis, the orientation of the planet's powerful and complex magnetic field, is itself tilted approximately 8.8 degrees from Jupiter's rotational axis. The approach trajectory of 3I/ATLS was not just heading toward Jupiter, it was heading toward Jupiter at an angle that would bring it into precise alignment with the planet's magnetospheric structures. The closest approach, based on the most current orbital calculations, was estimated to occur at approximately 420,000 kilometers from Jupiter, placing the object directly within the outer boundaries of the magnetospheric structures associated with the Io flux tube system. Closest alignment with these structures was estimated to occur around March 16th. Astronomers with access to monitoring instruments were watching that date very closely. There are several ways to interpret everything described so far, and it is important to be precise about what the data actually shows versus what it suggests. The jets firing at temperatures and distances where they should not be able to fire could potentially be explained by an unusually volatile composition, an object rich in carbon monoxide ice rather than water ice, materials with much lower sublimation temperatures that could remain active much further from the sun. It is not a perfect explanation given the intensity and geometric regularity of the jets, but it is a physically possible one that does not require abandoning known chemistry. The detector saturation event could potentially be explained by an unusual and exceptionally strong natural hydroxyl emission source, perhaps driven by an internal energy mechanism not yet characterized in objects of this type. The 8.8-degree trajectory alignment with Jupiter's magnetic axis could be coincidence. Improbable coincidence by the numbers, but coincidence is not impossible. The intensifying coma at increasing solar distance could reflect a complex internal structure, releasing volatiles through mechanisms not yet fully modeled. Each individual anomaly, taken alone, has a natural explanation that requires no extraordinary assumptions. It's the combination of all of them occurring simultaneously in one object that has produced the quiet but unmistakable tension running through the preliminary research communications surrounding 3I/ATLS. Scientists are trained to resist extraordinary conclusions. They are also trained to follow the data, and right now those two instincts are pulling in opposite directions. What is certain is this: 3I/ATLS arrived from interstellar space. It is the third confirmed interstellar object ever detected passing through our solar system, following Oumuamua in 2017 and Borisov in 2019. Unlike Borisov, which behaved largely as expected for an interstellar comet, and unlike Oumuamua, which showed non-gravitational acceleration but produced no visible coma or jets, 3I/ATLS is doing something neither of its predecessors did. It is actively outgassing at impossible distances. It is producing electromagnetic emissions strong enough to saturate purpose-built scientific instruments. It is following a trajectory that aligns with the most powerful electrical structure in the outer solar system with a precision that the mathematics struggle to accommodate as random chance, and it arrived at a moment when humanity happens to have a spacecraft already in transit toward Jupiter, already equipped with instruments capable of observing it, already close enough to gather data that no ground-based telescope could produce. Whether 3I/ATLS turns out to be an extraordinarily unusual natural object that is forcing us to rewrite our models of interstellar chemistry and cometary physics, or whether it turns out to be something that requires...
James Webb just revealed where we actually are in the Milky Way, and it changes everything you think you know. That sentence sounds like clickbait. It sounds like the kind of exaggerated claim that gets thrown around every time a telescope takes a pretty picture of a distant nebula. But this time, it is not an exaggeration. This time, the data coming back from the most powerful space telescope ever built is forcing astronomers to redraw the map of our own galaxy. Not a distant galaxy billions of light years away, our galaxy, the one we live inside, the one we thought we already understood. And the reason this finding hits differently from every other space discovery you have heard about is because it does not just change what we know about the universe out there, it changes where we are within it. For most of human history, we had absolutely no idea where we were in the galaxy. Not in the philosophical sense, in the literal, physical, measurable sense. We could see stars, we could count them, map their positions, calculate their distances one by one, but the actual structure of the Milky Way, the real shape of it, the true size of it, our precise location within it, remained genuinely unknown for far longer than most people realize.
defies. And the reason is almost embarrassingly simple. We are inside it. Trying to map the Milky Way from Earth is like trying to draw an accurate map of an entire city you have never left from a single street corner, while most of the buildings around you are hidden behind thick fog. For centuries, we made our best guesses. For decades, we thought those guesses were close enough. Then, James Webb turned its mirrors toward the heart of our galaxy, and what it showed us forced astronomers to go back and rewrite the map from scratch. The standard model of the Milky Way that most of us grew up learning describes it as a barred spiral galaxy, a flat, rotating disk of stars, gas, and dust, roughly 100,000 light-years across, with a dense central bar of older stars cutting through the middle of the disk, and several spiral arms curling outward from the ends of that bar like the arms of a slow-motion pinwheel. Our solar system sits in one of those arms, a structure called the Orion Arm, positioned roughly 26,000 light-years from the galactic center. That number has been in textbooks, documentaries, and NASA press releases for years. We were told we live in a quiet, suburban region of the galaxy, far from the violent, crowded core, tucked into a minor arm between two larger primary arms. It was a clean, comfortable, orderly picture, and according to what James Webb has now sent back, it was more incomplete than anyone had publicly admitted. James Webb is not like any telescope that came before it. The reason comes down to one thing: what kind of light it sees. Every major telescope humanity built before Webb, including Hubble, was primarily designed to observe the universe in visible light, the same narrow band of the electromagnetic spectrum that human eyes can detect. Visible light is useful for an enormous range of observations, but it has one devastating weakness when it comes to studying our own galaxy: dust. The Milky Way is filled with vast clouds of gas and dust that absorb and scatter visible light, creating regions of the sky where visible wavelengths simply cannot penetrate deeply enough to reveal what lies behind. The galactic center is almost entirely obscured in visible light. The dense, star-forming regions of the spiral arms are wrapped in dust clouds that block optical observations completely. For decades, these dusty regions were the blank spaces on our galactic map, zones where we could make educated inferences but could not directly observe what was actually there. James Webb sees in infrared light. Infrared wavelengths pass through dust clouds the way radio waves pass through walls. The dust that was effectively opaque to every previous telescope becomes essentially transparent to Webb, and when Webb pointed itself at the regions of the Milky Way that were previously invisible, it did not find what the models predicted. What Webb revealed in its deep observations of the central galaxy and the dense inner spiral arms was a level of structural complexity and stellar activity that the existing models had significantly underestimated. The central bar of the galaxy, that elongated, dense concentration of older stars cutting through the middle of the disk, appears to be both larger and more massive than previous measurements had suggested. Stars that were expected to be spread diffusely through the inner galaxy were instead found concentrated in structures and clusters that implied a completely different distribution of mass in the galactic interior than the models had accounted for, and the implications of that single finding ripple outward immediately. The mass distribution of the galaxy determines its gravitational structure. The gravitational structure determines the shape and stability of the spiral arms. The shape and stability of the spiral arms determines where regions of active star formation are located, and the location of those star-forming regions determines, over billions of years, where stars like our Sun end up sitting. Adjusting the mass model of the inner galaxy is not a minor correction to a footnote in an academic paper. It changes the address. Beyond the structural findings, Webb's infrared observations revealed something else that cuts directly to the heart of this story. The galaxy is not a stable, slowly rotating, orderly structure that the textbook diagram has always suggested. It's dynamic in ways that were not fully appreciated until an instrument precise enough to see through the dust could actually observe what was happening in real detail. The spiral arms are not rigid, fixed structures like spokes of a wheel. They are density waves, regions of compressed gas and stars that move through the galactic disk like a slow ripple moves across the surface of still water. Stars enter these arms, get compressed, trigger bursts of new star formation, and then gradually pass through and out the other side over timescales of hundreds of millions of years. Our solar system has passed through spiral arms multiple times in its 4.5 billion year history. Each passage brought us into denser regions of gas and dust, potentially affecting Earth's climate, altering the flux of cosmic radiation reaching our atmosphere, and possibly influencing the timing of mass extinction events preserved deep in the
the geological record, Webb's new observations of the arm structure nearest us have revised the estimates of how dense those passages were and how recently the last significant one occurred. We are not sitting in the same quiet, unchanging neighborhood we thought we were in. The neighborhood itself is moving, and we've been passing through more eventful regions of it more recently than anyone had previously calculated. There's one specific finding from Webb's observations that has attracted the most significant attention among researchers, and it concerns the Orion Arm itself, the arm segment our solar system currently calls home. For years, the Orion Arm was officially classified as a minor spur, a small secondary feature branching off one of the Milky Way's 4 primary arms. Rather than being a primary arm in its own right, it was considered a relatively low-density, low-activity region of the galaxy. That classification fit neatly with the broader narrative of our solar system occupying a calm, stable, sheltered location, the kind of quiet corner of the galaxy where life has enough time and stability to slowly develop over billions of years without being constantly disrupted by violent stellar events. Webb's new infrared survey data of the Orion Arm's star-forming regions have complicated that picture considerably. The arm contains significantly more active star formation than the minor spur classification ever implied. The density of young massive stars, the distribution of giant molecular clouds, and the overall structural coherence of the arm all point toward the Orion Arm being a far more substantial feature of the galactic disk than it was previously given credit for. Some researchers working directly with the Webb data have argued that the entire distinction between primary arms and secondary spurs in the Milky Way may itself be a simplification the new data no longer supports. The galaxy doesn't organize itself into 4 neat arms and a handful of minor features to match the clean illustration that has appeared in every astronomy textbook for the past 30 years. It's messier, more complex, more alive, and we're sitting deeper inside its active machinery than we ever realized. So, what does all of this actually mean for the question in the title? It means that the address we've been giving ourselves, 26,000 light-years from the center, minor arm, quiet suburbs of the galaxy, while not precisely wrong, was a significant oversimplification of a location that is far more dynamic, far more structurally important, and far more embedded in the active ongoing processes of the Milky Way than we previously understood. It means that the specific combination of conditions that made our corner of the galaxy a viable place for the development of life over 4.5 billion years is more finely tuned to our precise galactic location than the old model ever suggested. And it means that when scientists ask whether complex life could exist elsewhere in the Milky Way, the answer now has to account for the fact that finding a star with a rocky planet in a habitable zone is only part of the equation. That star also needs to be in the right place in the right arm at the right point in the galaxy's history, with the right combination of radiation environment, orbital stability, and star formation activity to allow billions of years of uninterrupted biological development. Webb's new picture of the galaxy suggests that the specific combination of factors present in our exact location may be considerably rarer than the simplified model made it appear. We didn't just get lucky having